Continue.
Okay.
Welcome for the pre-comprehensive exam. Sorry for the delay once again. And we have Dr. Ananda, Head Advanced Aerospace Electronics Division, and Mr. Dr. Shiv Subbarao from NILS internal member, and Professor Narendranath from NIT Surat, and Professor Vijay Lakshmi from Bagalkot College of Engineering. Welcome you, sir. Welcome all of you. Actually, I'll just give the brief background. Actually, the student joined in 2009 and he completed the coursework in 2019. And we started the experiment. Unfortunately, due to COVID, it was there's delay because students are not allowed those issues. Now, but in between he came and he conducted some experiments and he started the modeling and all. Those results we will present to you, and we look forward your guidance and approval for proceeding in this direction or any other suggestion. So we'll start the presentation now.
So that's quick, yeah. We should talk to. Yes, quick. Talk to. Tell her you want to get the. First time for you.
Yes, sir.
You should come 1 hour early. We keep pads. I asked him whether number of pads, everything.
And give a brief to Professor. Yeah. So I'm telling preparations are required. HD pre-com cannot go like this. You prepare 1 day before.
So, work we prepare.
No, these conferences, counting.
Good afternoon, madam. Professor has quit the meeting. We are just confirming from him. I'll keep all of you on hold, please.
Okay, sir. Sure.
Yeah.
No issue.
Sir, good evening, sir. Sir, good afternoon. I'm Sendil Kumar once again. Sir, sorry for the inconvenience, sir. Can you join? Okay. You will join, sir? Okay, sir. Okay, please, sir. Huh? Thank you. Thank you. Mouse.
No, where are you typing? We are typing. Happening.
All are asking about that.
In there only.
Sir, we need to
First open there.
Yes, sir. Yes, sir.
You come here.
I will come. Okay.
You think that he's starting it.
Now we will start the presentation.
Can you please confirm? Can you see the presentation, please?
Yes, sir.
Okay, well,
Yes, sir.
thank you. Yeah.
Good afternoon, my respected sir, my DC committee members, and myself, Arunabh Datta. Actually, I am doing my PhD under the guidance of Dr. Senthil Kumar Palaniswamy sir, and my research center is CSIR National Aerospace Laboratory under the VT Visvesvaraya Technical University. So my topic is modeling and failure prediction of safe memory alloy using advanced signal processing. So just a minute. Yes. So this is my outline of my today's seminars. So first is what is safe memory alloy, then applications and advantage of safe memory alloy, then literature survey, research gap of that in safe memory literature, then research objective, then experimental setup and measurement. And based on experimental setup result, then we develop some algorithm for modeling, then algorithm validation and conclusion and future scope of the work. Just a minute, sir. Mouse pointer. Yes, sir. Yes, sir. So this is very basic. If I am talking about safe memory alloy in crystal structure, there is two type of crystal structure. That is, one is BCC structure and another is FCC structure. So BCC structure or high temperature structure austenite phase, that is the austenite called austenite, and FCC phase centric cubic, that is your martensite phase. So first in the left side we can see this is the austenite versus temperature effect, that is the temperature when we are starting here, austenite start, then we are increasing that, then when we are go for 100%, that is austenite finish temperature, then when we release the temperature, then it's coming to the martensite start, then it's down decaying, so martensite finish. And in here we can see that is the austenite start, austenite finish, martensite finish or martensite start. These points are different positions, not coming into the same point. So there is a large hysteresis is present here. So this is the first, that is the temperature effect in safe memory alloy. Then another thing is when we are talking about stress. Stress, so in austenite, when we increasing the temperature, decaying the temperature, that state is point martensite, means the BCC structure is going to start FCC structures. So that is called twined martensite stage. When we another time we increase the, okay, right, next. So this is the safe memory alloy. So that is the stress versus strain versus temperature. That is a 4 point. When you are twin martensite, then is when we increase the stress, it's going to the detwined martensite. Then another when it is coming to the another 0.4. Then when we are temperature heat recovery stage is there. So this is the involving stress, strain versus temperature of safe memory alloy. And here is the superelastic property of SMA. Okay. So advantage of SMA, that is the high strength that is the one advantage. Then high power to weight ratio, then large energy dissipating capabilities, and then high strain recovery. That is the advantage of SMS. So now talking about applications of SMA, so that is the applications of SMA, that is the thermal SMA applications, that is the Chevron's applications. Then we are coming to the biomedical clip, then stent also, that is the biomedical, then your civil application also, that is the we are using SMA wires. Then domestic applications like your spring, like this kind of domestic applications. Here one interesting aerospace application that is by our NL group, that is the landing gear of this is the one good applications of your aerospace applications. So next, this is the literature survey. So far I did so many literature survey, just I am here giving some reference for my literature. So basic from the consecutive models, from Brinson model, Tanaka models to our data driven model. So these are some my literature survey. So that is in my report. I have already put it that literature service. Then coming to the characteristic behavior of SMA. So first thing, fatigue from cyclic loading cause deformations. That is the one good characteristics of SMAs. Then degradations. For degradation, damping occurs when it's exposed to cyclic strain. Then overstress, load above the 8% strain could be caused to SMA completely lost it austenite phase, so or austenite shape. Then difficulty of large data computing, that is the main thing. Difficulty of large data computing means here we are doing after SMA data, so data computation, it's very complexity is there. Then high cost SMA nickel titanium material we are using, that's why it is high cost material. So now coming to the consecutive model of SMA. So modeling, when we are talking about modeling, so there's an example of modeling of Brinson model, that is basically advanced version of Tanaka models. So there is a lot of equations is there for Brinson modeling. So we are going for the consecutive modeling. We are going for data driven modeling. So data driven, if we are going for data driven model, so actually here cumbersome, so mathematical equations, that type of equations is very cumbersome or complexity in our modeling. So that's why we are going for signal processing methodology for modeling the parameter based on physical or physics based modeling. So that is my research objective. So first is carried out experiment SMR under cyclic loading various frequencies to analyze and understand the behavior of SMA, then developing model for single cycle hysteresis cycle using system identification, feed forward network, then neurophagy interference or ANFIS, then deep learning algorithms. Then developing model for each frequency, low cycle fatigue data to which we have experimental conducted, then low frequency estimation using high frequency model, and high frequency estimation using low frequency model. Then the next part is another failure prediction, that is through system identification, feed forward neural network, then neurophagy interference system, deep learning algorithm also. So this is the facility available in our research center. So for our experimental, we use that is the experimental setup of our SMA testing. So specification in our experiment, that is the 54.3 nickel and 45% by weight, that is the titanium. Then diameter of testing wire, it is 0.6 mm, and before test the sample it is heat treated and temperature to 500 degrees centigrade for 15 minutes, then water is quenched, and these are the DSC result for your temperature of martensite finish, martensite start, then austenite finish, austenite start, that is the temperature DSC reports. So in our here the input displacement, so input displacement actually 1 to 6% amplitude displacement in millimeter, that is the strain actually. So here we can see the from 0 to start, then maximum is 6%. So we are varying, so that is the 1.5 to here 1.5 to 6% input displacement. Here we can get the hysteresis loop of our various frequencies. So in hysteresis loop, we can easily find that when we increase our frequency here, then the hysteresis loop is going to slow down. So reducing in manner. So we can say 1 hertz hysteresis loop is greater than your 25 hertz frequencies area under the curve. So that is the based on this we can find the energy dissipation in my last result. So this is the experimental measurement. We can see the 1 hertz, that is the strain is 6% and or 60, and that is the stress. So and hysteresis curve also there 1 hertz, then there is 5 hertz, then 10 hertz, then 15 hertz. We can easily see in that here the area under the curve or hysteresis is going to decaying, that is in level when we increase our frequency. So that is our 25 hertz and 20 hertz. 20 and 25. So now it is the frequencies of 1 hertz, 5 hertz, 15, 20, 25, and the failure point. So far we are concluding the failure point and failure cycle range. That is the 20%, 30% error is there. That is the failure cycle range of our SMA in our experiment. So now it is the typical representation of measured 1 hertz cyclic data. So in our cyclic data, we analyze that thing. First part is transient part due to deformations of material or materials changes. Then middle part is stabilized or oscillatory part. Then after stabilizing and oscillatory part, there is a failure part. So this is a typically 1 hertz full cycle data. So based on this paper, Lawrence et al. Paper deformations mechanism, they are also doing that thing. That result they are doing in 3 cycles, 3 parts. That is the first part that is. Then second part is 40 cycles, and then perform until failure here. Last part is the failure part. So based on this method, we are concluding our experiment modeling like same manner. So we are segmented our data for modeling. So that is the one that we are taking first 10,000 data point for transient phase. We can easily see that transient is here. Then 10,000 data for your oscillations part. That is the fixing the oscillations part. Then failure part we can see in last 10,000 data point here failure occurred. So data used for modeling and validation. So 10,000 data we are taking for as a input data 5 hertz and 10 hertz for 1 hertz model, and testing purpose we are here testing 15 hertz, 20 hertz and 25 hertz our testing data. So model for high frequency model, we are taking 25 hertz data frequency data as a model data. Then input data is 15 and 20 is our input data. Then testing is 1 hertz, 5 hertz and 10 hertz our testing data. So now coming to the different algorithm proposed in this work. First is system identification. So system identification, there are lots of system identification method is there, but we choose here a Hamilton-Wiener method for system identifications. Then deep learning algorithm. So GRU, get a neural recurrent unit, that is a GRU algorithm we are using. Then NFIS and feed forward network we are proposed for our work. So algorithm development based on system identification. System identification is just like your transfer functions method. So here we can see the UT is our input of the system. Then input is non-linearity. Then weighted is WT. Then linear block is there. Then XT and output is non-linearity. When input is not present there, that is the Hamilton system, and then output is not there, we can say that is the Wiener systems. So this is the actually model output for 3 different stages. So we are computing that WT equal to F into UT from input data, where WT is an input of the linear transfer functions of, that is the B by F or block diagrams. Then input non-linearity is a static, we can say it is memoryless functions, where the value output is given times only. then compute the output of linear block using WT and initial condition that may be XT is our initial condition is BF into WT. Then we configure the linear block by numerator and denominator, that is the B and F. Then compute the model for linear block and using nonlinear function H as a T, YT equal to H into XT. And similar way as I told in non-linearity, the output non-linearity is a static functions. So we can also remove the output non-linearity such as YT equal to XT. We can for this manner we can remove that non-linearity of output. So that is the optimized hamster winner model. So for we did our optimizations here, we are using here algorithm. So that is the adaptive Gauss-Newton method. And here we can easily see the output is wavelet network we are using here. So non-linearity is output, and we are fitted 90% fitted our data for our modeling. And this is our transfer functions. Basically, that is the Bn and Fn and Kn is equal to 1, and loss function you can see here loss function is 0.1. So that is our based on our optimization hamster winner model. And based on this, we get some result. So estimation by that is the model output versus your experimental result output. That is the estimation is 1 Hz estimation model with compare with 1 Hz experimental measured output. We can see here the peak of the curve matches well. However, it's tough to exhibit the poor matches here. You can see in this the zoomed portion. So matching is not so good. So, but in signal processing manner, we can say more or less it is a matched. Then we are estimating that is the 1 Hz with compare with 15 Hz, and that is the zoomed result of 1 Hz and 15 Hz. Then it is my 1 Hz versus 20, and that is the 1 Hz versus 20 Hz. Here it is just squeezing the downward function. So next is 1 Hz versus 25 Hz. So that is the 1 Hz versus 25 Hz. So for we are getting this type of hamster winner model, we are not satisfied. So we are going for another method, that is the recurrent neural network or GRU method we are using. So GRU or recurrent neural network is basically kind of neural network which can remember the past input given to the and prediction based on the previous input as well as the current input. Means past, based on the past we can go for present also. So based on this recurrent neural network, we are proposing that GRU network. Just a minute. So this is the GRU unit. Okay, so GRU unit, that is the previous unit, and current unit, that previous unit and current unit, based on this we can go for next next inputs. So this is the basic algorithm of our GRU. So this is our model. Actually we are creating through Python or architecture, you can say that is the architecture of GRU model. So we are creating this PyTorch, or we are using basically Google Colab for this Python. So in this architecture we can say input is 10,000 and output is 10,000. Then dense node is also we are putting here 10,000 to we are reducing to 200. So last dense is 48 is their last dense. So how much network we are realizing in this architecture in GRU model, and the testing time it takes 5 minutes for this 10,000 data for GRU model. So we can see that is the training loss plot for the GRU model. So however our training losses versus or model losses versus your epochs, number of iterations, that is the 200, we can go for here to 200, that is the settled, but we are run our program for 1400 epochs. So now validation of our algorithm. So here we can see that 6 experimental data set, as I told you before, that is 1 Hz to 25 Hz. With a step of 5 Hz, then 6 data set we can modeling for 1 Hz as a target data for, that is the low frequency modeling, and input data is 5 and 10 Hz for training. And based on this creating we are GRU model and using we are Adams optimization technique. And then validation purpose we are high frequency data like 15, 20 and 25. We estimated the target rate of 1 Hz data. So this is our estimation result of 15 hertz. So experimental result and GRU model. So this is the zoom portion result of our GRU versus experimental result. That is for 20 hertz data. That is the zoomed data of 20 hertz matching. That is the 25 hertz, the experimental data and GRU model output. And that is the 25 of zoom data. So we can say that estimation is good, some good correction we can say as compared to our master winner. So this is look, this is the our hysteresis loop of GRU data versus just a single 15 hertz experimental data versus GRU model. This is the hysteresis loop estimations of our stress strain of your that is 20 hertz. Then that is the 25 hertz. So we can see here how when we increasing our frequency, we just reduce the hysteresis loop. So this is, as I told you before, the so dissipation energy we can find from this hysteresis loop, and that is the error is very maximum error, that is the 120 because we are getting this two from this 2 point we can measured and modeled. So summary of this, so SMA we are using nickel titanium. Then applications we can say our aeronautical applications we are using, then literature survey, so and then experimental demonstration, and this is the modeling of first one is hamster winner, and that is the GRU network of hysteresis loop. So from this we can conclude that GRU method is more than superior to our hamster winner. So this is our conclusions, our this thing. So nonlinear hamster winner model is not capable to estimate cyclic behavior of higher frequency, as we seen in higher frequency, that is not capable. So we can go for GRU based deep learning to estimate the cyclic behavior, that is quite accurately we can get from GRU models. Then three segmented we are three data we are estimated non-linearities, that is sigmoidal network, piecewise and wavelet network for our hamster winner. And here last is the effect of loading frequency on fatigue live SMA or superelastic shape memory alloy thin wire has been studied considering various loading frequency, that is 1 to 25 hertz, and area of hysteresis loop decrease with increase the number of cycles. Thank you, sir. Any questions?
So I think student has completed the presentation. Now I request the professors for questions and clarifications, please. Oh. Can you please hear us?
Yes, sir.
Madam, please go ahead if there are any questions and clarifications, please.
Sir, can you put the future scope or future slide?
Yes, yes.
Yes.
Future scope slide. So further, you will be modeling with a single hysteresis cycle, sir.
Yes, but actually transient response we are not modeled right now. We are just
Yeah.
middle portion and end part. We, as I shown in the diagram, 3 segmented means oscillatory part and the failure part. We are just modeling that thing. Transient part is we are not carried out. So from result data. So after transient part, we can develop model for single hysteresis cycle. And that is the system identification method. Then deep neural network and adaptive neurophagy interference system also we are using for that.
Okay. So for any application development, we can't consider the real-time conditions. So I think based on some assumption, this modeling process will be done, I think. So what kind of assumptions you have made to get these type of results with respect to your modeling?
Madam, basically, we are basically based on that is simple control system theory. We can say that is the based on the our frequency. We know that is the strain is our 6% and material parameter we are not considering for modeling here. We are considering input output, and based on this we can go for our future. So if we are our target is if we have any unknown frequency, like we have measured data 25 hertz. So if there is a 30 hertz data, then we can predict that data using that 1 hertz model or higher order model.
So a good presentation, Arnab. That's from my side. If any other members can go further ahead. It's okay.
Yeah, thank you, madam. And I think Professor Narendranath looks to be in a meeting. So I request Dr. Sandil to take his feedback once he is free. Meantime, Dr. Subbarao is here. I request him to give his comments.
Okay. With chairman permission, I want to put these questions to student. Okay. What is the reason you consider 0.6 diameter of SMA?
So actually 0.6 diameter for very thin wire SMA we are considering that 0.6 SMA. So
now you mentioned some of the applications in aerospace, domestic, and various applications.
Yes.
What are the types of SMS their use? Is you showed dental, biomedical, other things. It is not 0.6. It is different.
Yes, sir. So I just to conclude that is the maybe example of 0.6. That is the example means thermal SMA also. I have Severon also. I have included that thing.
No. I think the question expert is asking is, what is the basis of selecting 0.6 mm? You cannot, ad hocly select some, some measure the 0.6, 1 mm, whatever the wire you have, and then start experimenting. You should have objective. Why did you, what decisions made you to select 0.6?
No. Can I answer?
Yeah. Okay, go ahead. You just press.
This is basically we are selected based on the load, what it is going. For example, we have targeted for the blimp application. For the landing gear, what is the load is coming and what is the, when it is coming for stress level, what is coming. That's what our objective what is it, around 600 MPa maximum stress it has to be with candle. So we are selected as the 0.6 mm diameter.
Okay. Now you understood that for particular blimp application, you have taken the 0.6 dia. Okay. Now why you conducted experiment up to 25 hertz? In blimp, it will not go beyond 0.1 hertz.
Yes.
Yeah, good answer.
Actually, we are conducting different frequency for that hysteresis loop we are getting. So that's why we are conducting that experiment also.
No. Now you mentioned 0.6 hertz is taken for particular stress number. Okay. That stress number, when you take it, when you increase the frequency, definitely number of cycle it will failed. One of your table you mentioned 25 hertz failed in 2000 cycles, means fatigue life has come down.
Yes.
When you are doing the model, you have to go little realistic. Why you are doing the comparison of the model with 1 hertz, 15 hertz, 25 hertz? When the particular application, beam application requires 0.1 hertz or 0.2 hertz. You got my point?
Yes, sir.
Any answer?
Yeah. Actually, he is not explained that as what we are trying to do in the overall objective. Actually, we are trying to develop a generalized model system, whether it can predict for the various frequencies. Because it is going to fail in different cycles. But actually, if we have the generalized model, any frequency, whether we can apply and get when it is going to fail or what is the remaining life. Those things we want to estimate. So we are varying that frequency and doing the experiment.
No, my question is,
I'll come. We see, 0.1 hertz, when we take up that experiment, we have conducted the experiment, we have the data, but in the failure cycle also more, the large data, you see now itself we can see 1 hertz or thing, it is going to around 5 lakh data points. So 5 lakh data points or 0.1 hertz when we go, it will be around 6 lakhs or 8 lakhs data point. So the processing will be very difficult. So what we are telling for developing the model, we are taking little which is going to fail little early. So both process we want to induce result because whatever we are doing for the aerospace application, that is not part of his research actually. We are trying to develop our own model set. Later for our application, we will be using this research output for our application.
okay, then how you are going to tune for lower application is a question mark. Now I'm going to next question. What is the basis you taken 10 to the power of 3 data points?
But, okay, initial actual 10 to the power 3 data points we are taking for your initial stabilizing part, that is a transient part for 10,000 data point we are taking, then middle section we are taking for 10,000 data point, and failure and after
No,
failure
what is the basis?
What is the basis?
Why 10,000? You can lower frequencies, you can take 1,000. Higher frequencies, you can take load like that. Because this is engineering, no?
Yes, sir.
You can't keep one number for all frequencies. Now the frequency means data is coming very fast.
Yes, sir.
Okay, there you may require more data points.
Yes, sir.
Lower frequency means when the fatigue cycle is running at lower frequencies, you may require to sample it lower, and your data points also you are taking and overloading the machine by taking 10,000 points.
Yes, sir.
That is my question.
Sir, actually thing is that we are first our target is taking all data for modeling that thing, means 5 lakh data for 1 hertz for example. So that data we have to model for our whole system. So basic initial part, as I get one literature survey, so they are taking just part wise initial part, then mid section, and then end
No,
section.
it is understood. It is understood. Any basic or any paper literature is there. If you take 10,000 points, you will get the proper model. You do that literature survey as per my suggestion.
Yes, sir.
Otherwise, there is no point in doing your modeling with the 10,000 points. Okay.
Okay, sir.
Okay. Now you were mentioned that Hamilton model is not predicting at lower frequencies is going. My opinion is a good model, but your loss factor, if you consider, it is 0.1.
Yes.
Means it is loss factor is it is going above 10% range.
Yes, sir.
So that is the reason when it comes in the lower range and going to means any fatigue cycle, if you take it, it is tension and compression mode. Tension, compression.
Yes.
When it is going roaring up, the controller will take the full load, PID. When it is coming down, it is not taking the load. Basically, you are having loss factor of 0.1.
0.1.
You should investigate if we can reduce the loss factor still low and you try to match the data. That is my suggestion.
Okay, sir. Okay, sir. I will keep it in mind, sir.
Okay. So why another question generally basically why if a fatigue cycle increases why the material fail fast?
Sir, material failed fast because fatigue beyond some crystal structure, that is the deep change. For that case, we can say material fails. Sir. Some stress we are applying, and continuously we are applying that thing load. Then we are getting.
I'll answer that because when the frequency increases,
Yes, sir.
definitely in the material temperature rises.
Okay.
So you have to note at what frequency what is the temperature rise. It will lead to the material to fail you. Okay, when you take some wire,
Yeah.
you bend it. If you touch it, it will get heated up.
Heated,
You
yes.
taken. So my point is when you are doing the experiment, when it is more than 5 hertz, you measure the wire temperature and note it down according to that. It may help you for your models.
Okay, sir.
Okay. Thank you, Chairman.
Okay, so thanks. And can I quickly check if Professor Narendranath is back? Looks, I think, still he is busy. Okay, I think I have a few points before we get his feedback. My, I think, impression, of course, the first time I'm hearing this, this is the first meeting. I'm not seen a good literature survey report of this. Basically, a literature survey, you should identify the gap areas of the literature, not just one statement. You can't make that some algorithm is not meeting or not serving the purpose. But our literature survey should clearly bring out what are the gaps that we have, and when we define my problem statement, I should really fill that gap by solving, and we should aim at what is that we are targeting the results. But your literature survey is just a study. You have not brought out any facts and figures of the literature survey, at least in the presentation. That should be clear. Otherwise, you will do some experiment, and end of the day, we will not know what to do with the results. We should try to focus the experiment based on my requirement, or rather the objectives of the problem statement, number one. Second point, I think everywhere you have assumed so many factors and figures, but there is no basis for that numbers. Some 25 hertz, some time, some 0.6 mm, and there is the bandwidth or some data points, wherever it is. I mean, all numbers are assumed. I'm sure maybe you may have some reasons, but it is not brought out very clearly in the presentation. This has to be the very fact of the PhD is not to put numbers and figures in the PPT, but the basis and reasoning is something that which should be implicit in the research work. So that should be brought out very, very clearly, because otherwise the experiments can happen, but you will get results. But to make a decision, it will be a thing. Now, you have done experiments at room temperature. Correct? Yes. So, what would happen at a varying temperature? Where is your model? How does your model take care of the environmental effects? So, because it is very sensitive to that, no?
Yes. SMA is sensitive to temperature.
In a mid.
So, what is your approach? What have you done for that? You have done anything or no?
No.
Okay, so you have to address that. Otherwise, we cannot. See, one thing is very clear in PhD work, research. We should not conclude before we experiment all the factors which will influence. Okay, so otherwise it will be a wrong conclusion that we are making. Some algorithm is working correct at a very constrained, benign conditions. The same thing you take it outside the lab, it may not work also. So I think the coverage of the boundaries to be very, very clearly thought about. Otherwise, we'll be making a wrong decisions, wrong explanations. Now, what is the objective? End of the day, okay, problem statement. I could not see the problem statement. Your objectives are like activities. PhD work should have the problem statement and the plan of action, what you want to do. But your objectives are only like experiment. Do this, do that, do this, and bring out some analysis. I think the approach to be changed. That's what I feel. It is not a master's topic. It's a research. A strong justification for the problem statement. Can you summarize what is your problem statement? What do you want to do? Not experiment. Experiment you keep doing. Experiment is a subset of your which aid to achieving, solving the problem statement. What is your problem statement as a PhD?
Sir, first of finding the failure cycle prediction also one thing, that is the here SMA.
So can I ask you, suppose nobody has done the failure cycle prediction so far? I want student answer.
So not so much, sir, failure prediction.
No, you have not found any paper on the predictions. In NL itself, many experts are there. This domain, NL itself, has experts.
Yes, sir.
I don't agree that there are no papers. So what is your over and above? Assume that there are papers. What is your contribution to enhance the properties? Enhance whatever you are telling. The failure, your topic is on the failure prediction. Okay, modeling and failure prediction of shape memory. So using advanced signal processing techniques. In your presentation, I could not see any signal processing techniques. What is the signal processing techniques we are adopting? What is its the unique features of it? What novelty are we bringing into the statements? That should be done. Otherwise, it is just an experiment. So I think somehow I am not convinced with the. I'm sure you must have done experiments. We really appreciate that. But as a this is a doctoral committee, so the committee should see the innovative objective and the activities accordingly. So at least explain what are the advanced signal processing techniques you want to follow. ML, this, that, neural network, these are very common words. What uniqueness you want to bring in as part of the signal processing? Because you yourself said, if I go in a different approach, it's a complexity because of a lot of equations and things like that. We agree. To simplify that, you are coming to signal processing.
Yes, sir.
So what is your unique techniques or proposals in signal processing you want to implement?
Sir, system identification method that is the part of signal processing. So far we are using that actually. Then we are getting that result. So then my guide suggested me go for any other signal processing technique. So
what is that identified?
So that is the we are not getting the exact hysteresis loop or failure. So that's why sir told me go for another processing techniques. So
No, which processing? Have you identified any method? Because identify.
So basically, sir identified, and that method is like your neural based, because the past event based on past event we can predict the future event. So then we are go for your recurrent neural network. So RNN, then we are go for deep inside in RNN, then we are go for GRU, greater neural network, that is GRU.
But still I'm not clear. Dr. Sandil, you can explain what is the advanced signal processing techniques we want to implement, and using that what we are trying to solve. Because I'm sure this is not a very new domain, that there are no precedences of this problem solving. There must be something, but we have to identify. I mean, my suggestion, if not done at least now, we should identify, and then we have to very clearly bring out my task as a research work, what we are trying to, what is the first problem statement identify. Towards that, what features you want to experiment, how you want to summarize, and what is your targets. Targets has to be clearly told. See, one not math working, other one working is a very qualitative statement. So there must be some quantitative assessment, and you have to define by data, this is what the enhancement I got over an existing algorithm, and how does it, and what are the boundary conditions of each of the experiments, and any assumptions that you have made. Is assumptions valid, realistic? Should we validate the assumptions? These are the things we should look at. And since this is the beginning of the thing, we should really address all of them. Otherwise, it is the doctoral committee's duty to give directions where and what's to be done. Yes, one is work which is done good, but at the same time, we have to address this. End of the day, this will be, this has to be presented, this has to be validated. Huh? This is my view. I think we should do that. Modeling techniques. Yes, still we have time to go. Changing this title also, but see, the words we use, you should justify, no? Okay. So this is how it is. So anyway, I think we'll have to take. Professor Vijayalakshmi, madam, do you have any further comments?
It's okay, sir. Not for now.
Okay. Thank you, madam. Thank you. So I think I request Dr. Sendil to take feedback from Dr. Narendranath, who I think looks to be, professor is still looks to be in meeting. So please take his feedback offline and maybe summarize all of them. And we need to have close, coordination and the guidance to the student. A lot of things has to be updated, and he has to come back. So probably he can come. When is, as per VT, what is the next meeting? When is the next meeting? 6 months.
Next meeting can, after the second seminar, first seminar you can have. Second seminar could be 6 months different.
No, but I suggest, because a lot of gaps are there, maybe in the next 1.5 months, you call for one more meeting, and whatever questions that we had today, that need to be very clearly understood by the student, and he has to come back with what is the plan of action. Okay? With that, I think I thank all the members, experts from outside, Professor Vijayalakshmi Madam and Professor Narendranath, Dr. Subbarao from NAL, and Dr. Sendil, the supervisor for this thesis, and of course the student who has made the presentation. So we will summarize and give you the minutes of this. I request both the professors and Dr. Subbarao to provide feedback, and then we can put it as a follow-up actions and guidance for the student who can continue the task as defined. So with this, I'd like to thank once again all, and we can close if there are no further questions and clarifications. I request both the professors to review the minutes of this doctoral advisory committee and give suggestions, even if it is not asked now. And while reviewing the minutes, you can please add if you think something need to be addressed by the student.
Yes, sir. Sure, sir.
Thank you, madam. Thanks, Professor Narendranath and others. So we will close the meeting now. Thanks and good day to all of you.
Thank you, sir. Good day, sir.
Good day.